Hey there, everybody. So let's talk about transforming logs. Let's make our power models into what we call a log model. So if we have a power model, and that power model is not quite linear, and we want it to be a little better linear than it was, we can take our power model, y equals a times x to the p. That's a power model. And we can make it linear, more linear, by taking the log of both sides. So I would take log base 10 of y equals log base 10 of a times x to the p. We can expand this log. We can expand it out. Remember, if we're multiplying, turn it into addition of two logs. Remember that from previous math classes. And then bring the exponent in front. So we can rewrite this as a log model, saying the log of y equals the log of a plus p times the log of 10. And remember, if we say log, we really understand it's base 10. Log base 10 of y equals log base 10 of a plus p times log base 10 of x. And if you look at this, you'll see right here that log of a is my y-intercept and p is the slope of my straight line. So that's pretty cool. Let's look back at our Atlantic Ocean rockfish problem. So in our last examples, we used the powers and roots to find a model predicting the weight of my Atlantic Ocean rockfish from its length. We still expect a power model of the form weight. This is still accurate. Y equals a times x cubed. Remember that? Predicted weight is a times the length of the fish cubed. And then here is the scatter plot of the original data. So we can see this is a nonlinear form. And then when we did, in the last video, we did this, it made a more linear scatter plot. So if we take the logarithm of both sides, let's take the log of length and let's take the log of weight. Here is the computer output and our regression line for that data. So I took the log of length and I took the log of weight. And look at this. Look at that beautiful linear pattern. And the residual plot verifies that linear pattern. Notice there's no pattern on my residual plot for the log of length, and the residual, it's all over the place. That lets me know that a linear model is appropriate. And then here is some of my summary data. They are telling me my y-intercept right here, negative 1.8994. And then the slope is 3.04942. And then I love this, r squared. Remember what r squared tells us? So 99.9% of the log of weight is explained because of the log of length. Can you get, it's going to be very difficult to get closer than that. So very cool. So go ahead, there's 3 questions for you to answer. I would like you to answer those 3 questions by hitting pause and then coming back. I'm going to show you those answers. Don't cheat. Try it on your own. Alrighty, so let's talk about our equation. Did you do it? So based on our output, based on the output, why would it be reasonable to use a power model? Why is this a good model? Well, when we look at it, the scatter plot of log weight versus log length has a linear form. Look how, remember, that has a beautiful line. And the residual plot shows a fairly random scatter of the points about my residual line. So a power model seems very, very, very reasonable here. The log of the length and the log of the weight, very reasonable. Look at that, beautiful. Well, let's make our equation from this data. If you didn't do it, try it, pause it. So we wanted to do the log, the predicted log weight equals negative. There's my coefficient right there, my constant. The constant is my y-intercept. Here's my constant right here. And my length, the coefficient in front of the length right here, that's my slope. That's, oh my goodness, that is how I made that line. Don't know why that happened. There we go. There's my slope. Come on, get with the program, Gilbertson. Now notice I use the word weight and length However, if you used y and x, you make sure that you define that y is my weight and x is length. I also like to always use my measurements. So I would have said y is the weight in grams and x is the length in centimeters. So if you did not use the words weight and length in the formula, make sure that you define them somewhere in the problem like I did in the last video. And then let's go ahead. Let's say they catch that 36 centimeter fish. Use that model to predict the fish's weight. So what we said is the log of their weight is, we plugged it in for their 36. I worked all of this out. Now remember, this is log base 10. So we can rewrite that as 10 times 10 raised to the 2.8464 power, and that gives me about 702.1 grams. If you don't remember what I did, remember the log of y equals x is really the log of base 10 of y is x. And this can always be rewritten as an exponent. Base to the exponent equals a number. So 10 raised to the x power. Oops, this should have been that's backwards. My goodness. So we wanted 10 raised to the x power. 10 raised to the x power. There we go. We wanted the base of 10 raised to this power equals this number. I had it written down backwards. Who do I think I am? So that's what we did here. We said the log base 10 raised to this power equals my predicted weight. So that's how we did that. So remember, you got to remember your log rules. So the base of log, if I just say log, we understand is 10. I mentioned this earlier. So if I say the base of natural log, ln is natural log, what is that base? Oh, the base of natural log, ln, logarithmique naturel, as the French say, is always the number e. If you want to know what e is, type e raised to the first power into your calculator to see the decimal estimate. It's like 2.7 something. It's pretty cool. I like e is one of my favorite numbers, even though I don't know what it is decimally. Now remember, when you are turning into a power model, we're going to start, if we're taking the log of both sides, which is what we were doing, we can use the definition of logs. Say 10 base 10, all of this is an exponent. 10 raised to all of this is the weight. Now we can further this up by talking about the power properties of logs. So because we have an exponent rule that says when we are adding exponents, that's really multiplying bases. Adding exponents is multiplying bases. So I made two 10s. 10 raised to this power times 10 raised to this power. Bring the 3.04942 into the power of x. Because if you have anything in front of a log, that means it's the power of what's inside the log. Then what we did is we can figure out what this is. 10 times negative 1.89940 is 0.0126 times, well, we have a rule that says if I'm doing 10 raised to a log, that's just the x portion, just this portion. So 10 raised to log base 10 is just the length. So this, we got this. Let me make my line a little fatter. This is there. And then we just bring this down. Boom. So this equation is now in our form y equals a times x to the p power. That's our power rule, which we just talked about. Notice that we got our 0.0126 and our power is about 3.04942, very close to the power of 3, which we said from the very beginning, which is what we initiated at the first part when we started talking about the rockfish. So very cool. All right. So what I'd like you to do is in your assignment, you should be able to do 5 through 8, talk about which models are appropriate, why are they appropriate, and estimating some values. Alrighty, so if you've got questions on any of these, remember I'll be back on Wednesday. Write them down, make sure I can address them. And I will talk to you on Wednesday.